Keep the correct color or right.
Good afternoon, everyone. Welcome to HiveMind, where we are looking at distributed file storage using JavaScript botnets. My name is Sean T. Malone. I am a principal security consultant with FusionX. Most of you have probably not yet heard of FusionX. We're a very small security consultancy. We focus on high-end penetration testing, red team assessments, a lot of sophisticated adversary simulation. If somebody with a lot of time, money, and talent were actually going to attack you, how would you hold up? What would that look like? How would your detection and response capabilities hold up? And so forth. We're definitely hiring, so if that sounds like something you're interested in, please talk to me after the talk. The problem that we're addressing here is sometimes there's data that we have on our systems that we don't want other people to see. And as we saw in this news article, and this is just one sample, there have been many similar items in the news lately, sometimes encryption is not enough. Even when you have something encrypted, there's always a key to decrypt it, whether that's a password, a hardware token, any sort of artifact there that can be extracted from you through extortion or some other means will provide the access to get to your data. So the idea here is to provide a means of storing data such that if somebody attempts to seize that data, it's gone completely. So the solution, store the files on someone else's system. So if your server is seized, the data is simply not there. Isn't that illegal? The answer is, in most cases, yes, it is. So that's why I started looking at JavaScript. The nice thing about JavaScript is that it's run in a browser, it's supposed to run there, but websites are able to execute arbitrary code. So we'll dig into that a little bit in this talk. So we're going to look at doing this with standard functionality. There are no exploits here. We're just looking at some tips and tricks and a framework, a methodology for how we can store significant amounts of data in a distributed fashion. So what we're looking at here are all features, not bugs. All of these techniques are used for real web applications out there, and there's nothing to patch. If we were to remove these features from web browsers, it would break a lot of the more modern web applications, because web applications are getting richer and richer, more and more complex. They can do more things, they can do it better and faster. This is great. It's what enables a lot of the rich experiences that we see in web applications these days, but it also provides a lot of very useful utilities that an attacker may be able to manipulate for their own purposes. So starting off with the disclaimer, this is a research project. The code is still very much in a pre-beta phase, and while I will be releasing the code, I don't recommend using it for critical data and something that you can't bear losing. Obviously, that's the idea, to get it to that point eventually where you would use it for data where you would rather lose it forever than have it pinned down on you and have somebody retrieve that data if they seize your system. The second component is that I'm not a lawyer and I'm not giving legal advice. And as with many things presented at the conferences this week, this can be used for evil. Don't do that. We've seen web browsers change a lot over the years. They start off with the most basic form of data storage on the client side, and that's the browser cookie. Then we have JavaScript for data processing, and that then leads to the AJAX, the asynchronous JavaScript and XML, where it's that background data communication between the browser and the server. This then leads to more advanced HTML5 technologies such as web storage, which is sort of like cookies on steroids, where you can store significantly more data in more complex fashions. Web workers let you spin off data processing threads that are separate from the application so they don't hang up the GUI there. And WebSockets let you establish the bidirectional communications. So again, it's sort of like new and improved version of AJAX. So the end result here is that a web browser has become a computer program that will communicate with my server, execute any code that I pass down to it, and store any data that I send. The end result is that you basically have a botnet node that's running on every system out there, every desktop system at least. You might look at this and say that browser sandboxing and all of the new security features built into these browsers, cross-origin policy, and all of these other items might make it difficult to access data and execute code. But the end result is that I really don't care about that. All I need to do is run code in the sandbox environment, store data in the sandbox environment, and retrieve it from there. So I'm not trying to read data from other sites. I'm not trying to read files off of your computer. This all exists within the normal browser security model. So again, there are no bugs here. This is all features. So let's look at what it takes to actually build a JavaScript botnet. As with any botnet, the first step is to actually infest the nodes. And there are a number of different ways that this can be done. Starting off with sites that you own. I own ShantiMalone.com. If somebody goes to ShantiMalone.com, it downloads the HTML, the images, all of the other assets from that server, and it executes any JavaScript files that are provided. So that right there is a potential injection point where I provide a particular piece of JavaScript that adds their browser to the node. Next is compromised sites, which is basically the same thing without permission. If you can find a cross-site scripting vulnerability, particularly a persistent cross-site scripting vulnerability, you can inject JavaScript or inject an iframe and add the nodes of whoever, or add the browsers of whoever visits that compromised site to your botnet as new nodes. URL shorteners are a fun one. If you go out and create a URL shortener, that sure, it displays the site that it was supposed to display, but it perhaps puts that in a full screen iframe, and there's another iframe on the page that's actually running the botnet code. Ad distribution networks. This is something that was discussed at Black Hat this morning. There are ad distribution networks out there that will allow you to provide an iframe URL or a JavaScript file that will be included with your particular ad. The usual purpose is to drive traffic to your site from many different IP addresses and boost your search engine rankings and such. But there's nothing to prevent you from putting whatever sort of JavaScript botnet code in that iframe as well. This is one of my favorite here, the anonymous proxy server. This is something that I've been working on, where you stand up an anonymous proxy server that's out there listening on the internet, port 8080, and it will be picked up. Someone will find it, someone will put it on the list of anonymous proxies, and people will start sending traffic through that server. And they're usually not paying attention to things like, are you modifying the server, or the traffic as it goes through that server? Are you injecting an iframe into every page that they visit? And this is a very effective technique to build a large botnet in a relatively short period of time. As an example benchmark on this, I have a proxy server that I've been doing some work with, where I stood it up, did not advertise it anywhere. It was just out there on the internet as an open proxy. And after a few weeks, it had been picked up, published on these lists, and I was getting hits from roughly 20,000 unique IP addresses in the space of 10 minutes. So it's a huge amount of traffic. Actually, I need to worry about having too much traffic going through there as opposed to not enough. For command and control, this is where the HTML5 WebSockets come in. This quote is from the official working group publication on WebSockets, where it says, the purpose is to enable web applications to maintain bidirectional communications with server-side processes. I mean, that could have been written to apply to botnet command and control type technologies. That's exactly what we want to do, to be able to push data back from the nodes and push commands down to the nodes. When that doesn't work, we can always fall back to Ajax, and that's something else that I've run into, where these browsers may be trying to connect with nodes, but for one reason or another, they don't support WebSockets. It won't get through whatever proxies they're going through on their end. It won't get through the particular technique that you're using to infest the nodes, such as if you're using that anonymous proxy technique. Sometimes WebSockets don't play nicely with that. So it's good to always be able to fall back to the more old school Ajax technologies. For data storage, we're looking at HTML5 web storage. Again, this is something where it says it's designed for storage that spans multiple windows less beyond the current session. Web applications may wish to store megabytes of user data. Why have it be user data? How about my data? On the back end, it's a Ruby on Rails application, though you could use any technology for this. The data storage on the back end is MySQL for the active record component, simply because it's easy to use. It's extremely easy to prototype web applications using that framework. But as I got into that, I realized, no, that's not really going to cut it for some of the types of data tracking that I need to do. So I brought in Redis as well, which is basically an in-memory key value storage. That's very useful for storing data that changes very quickly. It's in memory, so it's very fast. And you can set an expiration on keys. So if you have block data that you only want available for 20 seconds while you're reassembling a file, it's great to be able to set an expiration on it and have it expire and disappear as soon as you're done assembling that file. So that's an overview of how we can build this botnet and use it for, just have a botnet that we can use for any purpose. And I'm going to be looking at using it for data storage, but there's definitely more that you can do with this. Other botnet uses would be network scanning, DDoS attacks, or data processing through web workers. That last one is particularly interesting because anything that you can break up into individual tasks of data, such as password hashing, Bitcoin mining, anything like that, you can push out and have run in separate threads with web workers. So on a quad-core system, you can have 4 cores working to do your dirty work for you in JavaScript. And again, there's nothing out there to stop this. This is a feature of modern browsers. So we have a botnet. Let's look at what it takes to actually take that botnet and build a file system from it. Starting off with some definitions. A file block is what I use to simply refer to a piece of an uploaded file with a set maximum size. A node is going to be any browser that's a member of the botnet, and the server is simply the central command and control system that's used both to manage the botnet nodes themselves, as well as track the phone book, so to speak, for the files, the blocks, and where all of those blocks live. So storing a file. We start off with the basic file that's uploaded through the web application like any other file upload. That file consists of a name, the MIME type, and the file data. And this is a point where normally that would just be written to disk on the server or stored out in AWS S3 or some other type of file storage technology. But in this case, what we're going to do is go ahead and encrypt the data so that when we break this up and send it out, it's not possible for a malicious node to identify data that's being stored in these files. And then we break it into blocks, which basically means take that base 64 string of that encrypted file data and chop it into blocks of equal size. So what I found works well is 1,024 characters. It's a number that I pulled out of here. You could use pretty much any block size. You just need to make sure that it's small enough that you're not going to run into problems with the local storage maximum limits in the browsers, which is usually around 5 megabytes for most browsers. So this gives us a particular block that we can then store on the server. So take block 1, for example. We've got a server here that has block 1, and we want to store that out on our distributed file system. So we've got these nodes that have come in through the various techniques that we set up beforehand, and they're all checking back in, just saying, hey, I'm out here, I'm ready, do you have any work for me? We say, yes, go ahead and store this block. You push it down to the nodes, and you keep tracking your local phone book there on the server, what nodes have that block, and you do a hash of the block as well and store the MD5 or any other algorithm for that particular block, just to provide a basic sanity checksum. Was the data corrupted along the way? Did a malicious node tamper with that data and is trying to corrupt your file there? Over time, some of these nodes are going to go bad, whether this is malicious, intentional corruption, accidental corruption, or in most cases, nodes simply go offline. They will be visiting a particular website, going to a proxy server, and then all of a sudden they're not. What happens then? We start to lose these nodes, and so these nodes are constantly going to be doing a heartbeat check, where they submit data to the server that says, here's the list of the block IDs that I have, and here's the list of all of the checksums, the MD5s for all of these blocks that I'm storing. And the server is then tracking the expirations on the various nodes for each block. And this is another thing where Redis comes in very handy, because the heartbeat on the back end is simply updating the expirations on those particular keys in the data store. At any given point, if the number of live known good nodes falls before a certain threshold, it then pulls in new nodes from the botnet, sends the block up to the server temporarily, and replicates it over. Again, it has to go through the server because JavaScript can't do peer-to-peer communications, at least within a browser. Definitely Node.js and other systems can do that just fine. But within the browser security model, you can't actually listen on a port. So we have to send it back up through the server, but we write that block data to Redis with an expiration, it gets replicated, the block expires, and the data is no longer on the server. Retrieving a block looks very similar. We have it on all of these different nodes. When the request comes in to retrieve a particular block, the server sends out a request to all of the nodes in the phone book for that particular block saying, hey, send me this data, and the particular node sends it back up, and again, it's stored in Redis with a particular expiration time. And all of these nodes then come back up to the server, and then we can start looking at retrieving a file. So these requests go out, all of the blocks are sent back up to the server, stored temporarily in Redis, and then there's sort of a polling of the Redis data store to say, are all of the blocks here? How close are we to having the complete list of blocks? And once that's done, those blocks are simply concatenated into the encrypted data, feed that backwards through the AES decrypt, and you have your name, MIME type, and the data from your original file. And that provides us with a file that can then be downloaded. I'd like to pause here for any questions on this, since this is really the guts here. This is the part that's actually the distributed file system. Any questions on this component? Yes?
What have you found is your average time for a node to stay alive for?
Repeat the question.
The question was, what's the average time for a node to stay alive for? I don't have statistics on the exact average time, but it's basically going to be the average time that somebody is viewing a web page for.
Have you seen it, like, I mean, not in like scientific evidence, but have you seen something like, you know, relatively good attention in terms of like nodes?
Depending on the particular node and the type of data that it is, it's going to be anywhere from 10 seconds to 10 minutes usually. The interesting thing there is that, especially when you're going through an anonymous proxy server or something like that, multi-tab browsers, you've got all of these different systems, or all of these different sites that are being loaded in the browser. They're all going through the proxy, and the JavaScript is injected into every tab. So all of these different tabs serve to register this botnet, and they're all sharing the same local storage because it's all done in an iframe, so it's all in the same origin for this particular node. So even as you're closing tabs, browsing to new ones, it's still continuing to do that heartbeat and update the block expiration. So that node stays online until they completely close the browser or stop going through the proxy or something like that. Yes?
Did you do anything special with cache control or anything to make sure the files are staying there for certain periods of time, or were you just like the web browser can handle the cache control?
The question was around cache control and anything special that needed to be done there. For the anonymous proxy, I simply disabled caching so that it was getting fresh versions of the files. Particularly any time that I wanted to inject data into the site, a 304 response is not going to be very helpful there. I really need the server to be giving back 200 so that I've got the data flowing through there. But it's a very straightforward procedure to simply strip those cache-related headers from the upgoing request and then modify the data as it comes down. Yes?
This might sound like a stupid question because what technologies are now more so, but it sounds almost a little bit like mentoring in a way. Do you have any kind of way to determine if there are particular
on the seed nodes that will reliable and be able to provide blocks to your details into the botnet that you're trying to redistribute your blocks to.
The question was whether there are any particularly reliable nodes or super nodes that could be used to source the blocks from. I don't make a differentiation on that. It's probably possible to do that, do some statistical analysis of the nodes, how long they're staying online, how reliable the blocks are that they're sending up. But right now I simply send out data or send out a block request to all of the nodes that have it. Whichever one responds back first writes that key, and because I'm doing that MD5 check server side, it's known good data. So faster nodes are going to reply faster and make it easier to replicate that block. But I've not made an attempt to specifically designate super nodes for that purpose. Yes?
Two questions. First, who is performing the encryption and decryption of the data? And second, I don't know much about Redis, but is it a centralized server?
So the encryption and decryption of the data is performed on the server, is performed in the web application between when the file is uploaded and when the file is split into blocks in order to distribute it down to the nodes.
So if someone gains access to the command and control server, they automatically gain access to all of the data?
For some understandings of gain access, yes, and that's something that I'll get to on the next slide.
Sorry.
Then I'm sorry, what was the second question?
Is Redis centralized?
So Redis is a software program that runs on the same server. It's a data storage technique, the same as in a normal database.
So if you're caching that file on the server, what is the point of splitting the files out?
So I'm only caching the file on the server for a very short period of time. That's the purpose of the expiration keys. So when the file is uploaded, it does need to live on the server for long enough to encrypt it, break it into chunks, and distribute it. And then those blocks need to live on the server for long enough to be distributed as that replication occurs.
Unless the user itself uploads in blocks, in encrypted blocks that it itself encrypted rather than the server.
Right, it would be possible to modify this to do that, the encryption and splitting into blocks on a client and then simply send those up to the server in order to do that. What I was going for here was basically the simplicity component, that it's simply a web app where you go to this web app, upload the file like any other web app. There's nothing to install on your server, you can retrieve it from anywhere. Right. So yes, it would be possible to go that route. That's not something that I really looked into for this one, though. Yes?
I was curious if you're using any of the pub sub functionalities of Redis, because it seems like that might be really helpful in making this kind of platform.
I looked at the pub sub features for Redis a little bit. Didn't really find them to be necessary for this, but yeah, for future versions, that may be very useful. Yes?
Seems like the amount of network traffic going back and forth between the central server and the clients over time is going to be relatively constant value compared to the size of the blocks that you're storing. I'm curious what the network rate, general throughput ratio to the block size that you're storing ends up being.
So the question was on the ratio of the network traffic to the block size. The particular algorithms and interfaces that I've devised for this particular application have not been optimized in any way. So I'm sure there's definitely some bloat there that could be stripped out. In this case, the short answer is that I haven't analyzed it from that perspective, but there are definitely, there's a lot that can be tuned there in terms of the heartbeat frequency and the polling frequency for when you're checking for blocks that you want to send, because that's where a lot of the overhead is going to be. The actual block, the block storage and block retrieval, that's going to be very little overhead overall. It's simply an AJAX request, so you've got your normal headers and such there. It's going to be the polling every quarter of a second and the heartbeat every 5 seconds that's going to add up over time. Yes?
Web traffic is probably not going to be constant through the proxy. Do you have any method of isolating data on order of priority? So if the traffic volumes drop, say, for example, at 5 a.m. in the morning, one of the most essential ways to save on the solution?
Data prioritization is not really in scope for what I'm doing here. The solution there is to simply have a large enough botnet spread throughout enough different regions of the world such that people are going to be online in at least one region of the world at any given time, so you've always got a sort of critical mass. And that's the reason for having the replication. And you could even get a little bit more specific about it and deliberately replicate to certain areas of the world at different times. But the algorithms are going to handle that themselves to some extent, because as, say, Europe starts to go offline and those nodes go offline, the ones that are still online may be more in the United States, and so it's automatically going to replicate to those nodes that are still online. All right, so moving on to what happens when everything goes wrong. This is the whole purpose of doing this type of storage. There are obviously a lot of assumptions and limitations here, and so the question is why do this at all? It's really around server seizure. If somebody comes in and seizes that server, they unplug it from the wall and walk out of the room, and they're going to do forensic analysis, and they're going to get a court order for whatever encryption keys are necessary. That doesn't work in this case, and that's the beauty of this system, because nodes are going to go offline. They're no longer talking to this server because the server's not there. And as they go offline, block replication has failed. The server's not there, so it's not replicating to new nodes. And the blocks are lost, because as soon as all of the nodes go offline for any given block, the server has no way to retrieve that block. It's simply gone. And the files are unrecoverable. So when this server is seized, even if, again, based on that node lifetime of roughly 10 minutes maximum in most cases, the block is going to be lost after all of those nodes go offline. So say half an hour, and I don't know of any three-letter agency that's going to pull a server, analyze it in an hour, and realize they better plug it back in if they want to see that data. So obviously there are some things that could be done if you're going to analyze logs, if you're going to get logs from the ISP, anything like this, go out and find all of the nodes associated with those IP addresses and seize every single node in order to reconstruct this. That can be done technically, but it's definitely not feasible, and it's definitely not as easy as walking into a data center and seizing a single server. Yes?
Well, it's totally unrealistic to recover from that. Do you randomize your block IDs so that you don't store parts of the same file contiguously across, so that like, if they were to recover like individual pieces from like compromised hosts, they could just string together the IDs in order? And
so I'll show you that in the demo, but the block IDs are UID based.
Cool, okay.
So yeah, it's extremely difficult from simply looking at a block to know anything about the type of data there. The only thing that you could really do is I'm not padding the last block, so you might be able to say this block goes at the end of the file, but that's about it. Yes?
I would even argue that given those points right there, Redis is a better thing, because MySQL is going to persistently do stuff to disk, and that is recoverable, whereas Redis is free, and you have a lot better chance of
Exactly. That's definitely a benefit of Redis, since it's an in-memory key value store instead of something that's written to disk. Right. Redis does persist by default, so it is going to write to disk every so often to do the persistence. It's got better performance since the initial read-write is memory, but the persistence is something like you mentioned that can be turned off, and that's something that you'd likely want to do in this case. So right, it's all in RAM. You pull the plug, it's not there, and even if you do in-memory forensics while the server is still turned on, it definitely gets complicated there since you've already expired the blocks. That memory's been overwritten, and so on. I haven't looked at this from an actual practical forensic perspective, where I've given a server running this to a forensic expert. But the theory's pretty sound there, I think.
What they'll do is they'll freeze the memory and do a cold boot attack and do forensics on that.
Right. I mean, you can do a cold boot attack and get the RAM, but again, what you're getting there has likely been overwritten multiple times as all of this replication occurs. And if you're missing,
server's turned off.
I'm sorry.
I mean, once the server's turned off.
Right.
So
Yeah, and once it's turned off, the replication fails, and so forth. Yes.
So what's to prevent you from spinning up 1,000 different browser instances, getting all the data into these different instances, and then the three-letter agency seizing your server, turning it back on, and same browsers?
Nothing. Right, and you've hit on one of the weak points here, is that it is definitely possible to poison the botnet. It's possible, if you figure out how the nodes are being added, where that communication occurs, if you have enough nodes that are controlled by this three-letter agency, such that you then have enough of the nodes and you're logging all of that data, you have the phone book, so to speak, the directory of files and blocks from the server that you seized, and and again, because all of that is stored only in Redis, you would need to do the memory forensics there, and you would also have to find a way to extort that encryption key that was used to encrypt the file initially. But the feasibility of that, I think, is pretty low, and it's something that requires knowing exactly how that data storage is being done at the beginning. So that's something that you have to plan well in advance of seizing the server, as opposed to simply knowing this person is of interest, we're going to go seize all of their IT assets. Yes?
Do you have like a kill switch anywhere that like immediately as soon as the node goes offline, it wipes the local storage, or if you want to send a message to all of your connected nodes, wipe everything?
I haven't implemented that yet, but it'd be trivially easy to do. I currently wipe the data whenever you trigger a file deletion, but it'd be very easy to write something on the browser side as well that says, if you can't reach the server within 1 minute, 2 minutes, simply wipe all your local storage. So there's some interesting unanswered legal questions here. First is, can a website store significant amounts of data? Can they do this? Is this legal? Is this ethical? And this is very analogous to something like ads. If you go to a site, you're expecting that that site is going to try to serve up ads. Those ads may be flash ads, for example, so they're going to consume network bandwidth, they're going to consume at least temporary storage on your computer, and they're going to consume processing power. So I would maintain that what we're doing here is not any different than that. It's the same sort of thing. It's functionality that's in no way essential for the web application that you're intending to visit, and there is nothing that is actually illegal about writing data to a particular node. But again, that's not legal advice. That's just my own personal perspective on this. Same thing with bandwidth and processing power. This really comes into play when you start looking at the web workers for JavaScript data processing. If you're churning through CPU, and if you're going to make the computer a little bit sluggish, or if you're going to rack up their power bill, or on the bandwidth side, if you're paying by the megabyte or by the gigabyte, and you're using that node to conduct a DDoS attack, you're doing that with other people's checkbooks. So I think, especially ethically, there's a little bit more of a clear-cut problem with that. Legally, still a bit of a gray area if somebody did deliberately decide to go to a website and download and execute the JavaScript that was present on that site. Yes?
Have you tried this on cell phones at all?
I have not tried this on cell phones. There are cell phone browsers that support local storage, and I believe there are some that support WebSockets. So basically, any browser that supports this, there's no reason why it wouldn't work. It's just another computing platform.
It works really, really well. But you're limited to 5 megs of local storage on mobile devices.
I think the 5 meg limit is not just mobile devices. I think a lot of the browsers have 5 meg limits by default as well. The final interesting question here is the individual, is the end user, the owner of that node, responsible for the data that you push down there? If you're using this to store illegal data and you push down something illegal, and say for the sake of argument it's not encrypted, it's not even encoded, and you're storing missile codes or other types of data in the local storage on somebody's browser, and for something completely unrelated, their system gets seized, and all of a sudden this is in their temporary data in their browser cache, are they responsible for that? Because again, they did deliberately go to a website that served something down to the browser that got stored on their computer. This could be seen as similar to child pornography. If you went to a site that downloaded that, but you did not deliberately click save file to your computer, in most cases you're still responsible for having that on your computer at all. So this seems to be a rather similar case. Yes?
I think I have a slight issue with all these premises because, everything you're saying here, you're analyzing it similar to someone going there and downloading it. But if I'm on a website browsing, get ready to look for it, because I don't want to see data like I like to look for. But there's whatever I made that choice, I'm consuming it, versus you made an application that you're choosing to store on someone else's machine and they have no knowledge about. They're not choosing the JavaScript of the machine, they don't even know the JavaScript there. They're going to a website where you have their code is the intent is not the purpose of that website.
Correct. Yeah, there's definitely a difference of intent there. Whether you are intending to go to a site where the primary purpose of that site may be something illegal, as opposed to going to a site that happens to be compromised and is making your browser a member of this botnet. So if you can prove that it was unintentional, then you may be able to get out of it that way. But I think the default assumption is going to be that it was intentional.
Well, we assume that, but again, you're pushing the guilt on someone else. They're using a proxy rather than,
Right. I'm not claiming to have the answers here. I'm just saying that these are some interesting considerations with this type of data storage. Well, anyhow, let's get into the demo here because we don't have all that much time remaining. So let's see if this comes up correctly. All right, here's the web application where we basically have a list of files that we've stored already, as well as a list of nodes. Let's see if this will work. The Wi-Fi's been a bit sluggish here. Oh, come on. I know. All right, let me try switching over to the speaker Wi-Fi here. Anyone have the key for this network?
Say it out loud.
Should I check show password?
At least this way we get to know the length of the password.
Glad I had you type that.
I'm not sure I know it. There's a lot of them. Campaign sponsors, speakers, pressers, staff. Yeah.
Nice social media. back on the step.
But he's keylogging his own laptop.
There we go. There we go. All right, so this is a list of nodes that are active in the last minute. I am still troubleshooting the actual proxy injection technique, trying to deal with the massive amount of traffic that's being sent there and figuring out how to throttle the traffic in a way that doesn't throttle the botnet traffic as well. So these are mostly test nodes that I own that have been set up for this demonstration. You can see here we basically have an ID for each node, an IP address, the UID, which is basically how the browser remembers what node it is and identifies all of the traffic that's being sent back, and the last updated. So every time that request comes in, either a heartbeat or just a queue check to see if there are any commands, it updates that last updated time, and we use that to decide what nodes are we going to distribute to. We only want to attempt to distribute to nodes that are currently online. So going over to files here, the upload is very straightforward. It's just like any other web application here. Put in a password, choose a file to upload, and go. So it takes a little bit of time here because you've got to upload it and distribute it before it actually saves it. And here, this is pretty much the only information that's being stored. You've got, let me go into the detail view. You've got the file name and ID, the UID, but you don't even see the original file name or the type of the file. All of that metadata is stored in, it's just a JSON data store that's then encrypted and split up into these blocks. So here's the data that this file consists of. Here's what I mentioned earlier with it's all UID based. So you just have file block, dot, and then UID for that file. So this is all of the file blocks, and these are the nodes that they live on and when these nodes were last updated. So if any of these nodes, so the replication is set to 4 right now. Again, all of this is tunable. So it distributes to 4, and if it ever drops below 2, then it will go ahead and read that block in and replicate it to a new node. In production, you definitely want these values set higher since it's fairly easy to lose 4 nodes at the same time. And you can see it's a large number of blocks here simply because the block size is set to 1,024 characters or roughly a kilobyte. So going back to our file list, we can now fetch this file where you simply enter the password, and we'll do an incorrect password first just to show what that looks like. It loads the file blocks and says password incorrect. It's simply not able to decrypt that. So let's try again. And that is a legitimate loading bar in the sense of it's actually saying what percentage of the nodes have, or what percentage of the blocks do we have the data for. And the expiration time for Redis right now is set to 20 seconds, so if it can't get all of the blocks back in 20 seconds, it'll lose the ones that it has so far, and you'll have to just start the process over. Again, 20 seconds is just the number that I picked. That may be tuned differently in production. Putting in a different password this time. There we go. Seems the staff network may have bandwidth issues as well. Let's try this again.
Are those machines on Amazon clouds? You said you set those up yourself.
Yes.
They're on Amazon?
Yes. But you can put it anywhere. Yeah, it's just an AWS instance that's running this right now. All right. There we go.
What all web browsers have you tested this with?
This will work in modern versions of Chrome, IE, and Firefox. Those are the ones that I've tested. I have not tested it in other browsers, though anything that supports WebSockets and local storage is likely to work just fine.
Is modern IE setting it up?
Good question. I don't know exactly.
I think it's IE8.
I think IE8 and up for the HTML5 features sounds right. Let me try switching this over. Oh wait. No, all I have to do is threaten it apparently. There we go. Keep this. And there's our data. Obviously something that's becoming more and more dangerous to be caught with. Looking at this real quickly on the node side here. Here's an example going through the proxy. I went to my site, SeanTMalone.com. I've got Foxy proxy here that's set up to funnel traffic through my particular anonymous proxy server. And let's look at the HTML here. What I've done is simply replaced the ending body tag with an iframe right before it that loads the node in here. This node is nothing other than an empty HTML frame with the script tag to load our main application.js, and which is all of your jQuery resources and such, and the bot.js where all of the processing occurs. If we look at this in the console here, scrolling up a bit, we'll see here's where it's sending data back. All of these different requests here. This particular node is configured as an Ajax node in part because Firebug and others haven't quite fully caught up to show this sort of data for WebSockets. So it's nice to be able to see what's going on. So we see all of the different blocks being sent back there. And okay, yeah, I guess we're not showing the entries for where it actually stored this data. The check queue is exactly what it sounds like. Check the command queue, see what's happening. Are there any blocks to store? Are there any blocks that I should be sending back? Now let me go open that here. See if I can load this at all. Oh, you know, it'll be a bit hard to read on here anyways. If you're interested in seeing the actual traffic going back and forth, or if you're interested in digging into the code at all, I'd definitely be happy to do that in the question and answer session afterwards. That's about everything. Any other questions? Yes?
So, do you have any issues with detection from covert channel algorithm detection network? I mean, as soon as you start encrypting, as soon as you start making fixed payloads and heartbeats, you start to get that namespace and being able to detect
This would likely get caught by the right covert algorithm or covert communication detection algorithms. I haven't made any attempt to evade that, but again, the same evasion techniques, the same detection evasion techniques that work for any other type of data would likely work for this as well. Yes?
So are there any plans to increase the amount of time between, say, that block of data and how long before Reddit decides I need everything and points back to account, you know, maybe for nodes that might have like
So that's something where you could tune that on the fly. You could say wait a little bit longer than 20 seconds. You could make that shorter if you've got some high performance nodes. And that's something where the nice thing about the block retrieval algorithm is it simply broadcasts the message to every node. So for each block, you only need a single node that is going to reply fast enough. And so the easier way to account for that may be to simply increase your replication count so that you're replicating to more and more nodes, and you've got a higher chance of having one that's going to respond very quickly.
In that same thread, is there any thought towards increasing the amount of time between heartbeats?
You could. You could definitely increase the time between heartbeats. You could increase the time between these check queue commands. These are arbitrary numbers, essentially, that are all tunable via a configuration file. So it's something where, depending on the particular setup that you have, depending on your bandwidth, the size of the files, how critical these files are, and how you're investing nodes, because that's what's going to affect the quality of your nodes in general. But based on all of these different items, that's what's really going to affect how you want to tune those parameters. All right, well, thank you very much. And I believe there's a Q&A room for additional discussions.
Yes,
Is
there's
that
a
correct?
Q&A room down the hall.
All right, I will be there. Thank you.
About that.